So there's this new topic added to the AP curriculum a few years ago. It's called Photoelectron Spectroscopy, or PES. You need to be able to read photoelectron spectrums. It's basically a graph. I'll show you some examples in a bit. So here's what it involves. And again, it goes back to electron configurations. How do we know where the electrons are in an atom? How do we know that, let's say, lithium, for example, has an electron configuration of 1s2 and 2s1. Like, where did that information come from? How do we know that there's so many electrons in each of the sublevels? Well, that's where this comes into play. So this is an experiment, essentially, that led to the discovery of electron configurations. So here's what it involves. It shows the amount of energy needed to remove not just one electron, but it's actually all of the electrons from an atom. So the different amounts of energy needed to remove all the electrons from each of the sublevels in an atom. So energy in the form of X-rays or UV light is absorbed by the atom, and this causes electrons to be emitted by the atom, electrons to be removed from the atom. The energy of the light, which we can calculate using an equation we learned earlier. So E equals h nu. So the energy of the light is compared to the kinetic energy of the emitted electrons. So the electrons are moving off of the atom, and you can measure their kinetic energy. And then this difference, the difference between the energy absorbed by the atom and the energy of the electrons that are being emitted, is called the ionization energy. So really, we're looking at graphs of ionization energy. Very, very, very important, number 5. And this is going to be important later on as well when we talk about the periodic trends. Electrons that experience a greater attraction to the nucleus are going to require more energy to be removed. So we'll talk about the factors that affect this attraction, namely distance from the nucleus, as well as nuclear charge. The opposite is also true. So electrons that experience a weaker attraction to the nucleus will require less energy to be removed. Also very important is this idea of degenerate orbitals. Degenerate orbitals, that's a term describing this here in number 6, that the electrons in the same sublevel essentially have the same amount of energy or require the same amount of energy to be removed. So the 3p orbitals in the p sublevel are degenerate, meaning they have the same amount of energy. The 5d orbitals in a d sublevel are also degenerate. They have the same amount of energy. Something else that we'll see on the photoelectron spectra is that there's peaks indicating ionization energies, and the height of this peak represents the relative number of electrons in each of the sublevels of that atom. So let's take a look at some examples. Unfortunately, I was unable to copy over the one that you see on the left, so we'll start with the photoelectron spectrum on the right. So we see on the y-axis relative number of electrons. X-axis is the ionization energy. It's given in different units. Those units don't matter. Here it's megajoules per mole. Sometimes it's given in electron volts, or sometimes it just says energy. Now notice anything about the scale on the x-axis? Typically, scales will increase from left to right. This one increases from right to left. So let's take a look at these peaks, and let's see what they tell us about the electrons in this particular atom. Starting with this. Which electrons in an atom are the hardest to remove, therefore require the most energy? I'll give you two choices. Electrons close to the nucleus, or electrons far from the nucleus. Pause and think about that. So the electrons that are closer or closest to the nucleus require the most energy to be removed. So this peak here at about 126 megajoules per mole, that represents the electrons in the lowest energy level. Well, it looks like, according to these peaks here, that this atom has more than 2 electrons. So that peak represents the 2 electrons in the 1s sublevel. Take a look at that next peak at about 9 megajoules per mole. It looks to be the same height as the first peak. So again, the relative height tells us about the number of electrons. Well, we know that the 1s sublevel can hold a maximum of just 2 electrons. So the height of that peak there at 126, that represents 2 electrons. So the peak at 9 is the same height. It also represents 2 electrons. So which sublevel does that peak correspond to? That would be the 2s. So this particular atom has 2 electrons in its 2s sublevel. Let's take a look at the next one. Oh, before we go there, take a look, and it shows. So that first peak, 126, we have a big jump in energy for the second peak. That's why we have a break there in the x-axis. So why is this the case? Well, look at where the electrons are being removed from. It requires significantly less energy to remove electrons from a higher energy level than a lower energy level. So that big jump there tells us that we're removing electrons from a higher energy level. Electrons that are further from the nucleus, less attracted to the nucleus, easier to remove. So 9 versus 126. Take a look at that next peak. Not only is it significantly taller, so that means there's more than 2 electrons, it looks to be about 3 times as tall. So if the peak at 9 is 2 electrons, the peak at 5.31, maybe that represents 6 electrons. Notice the difference in energy. We go from 9 to 5.31. That is not a big difference in energy. What we can conclude here is that the peak at 5.31 corresponds to electrons in the same energy level as those corresponding to the peak at 9 megajoules per mole. So we're still talking about removing electrons from the second energy level. This time, though, higher in energy, so it takes more energy, or it takes less energy rather, because we're in a higher energy sublevel. That would be our 2p. So again, it's a higher energy sublevel, which means it is easier to remove electrons. Same thing with higher energy level. It's easier to remove electrons from a higher energy level than a lower energy level. Likewise, it is easier to remove electrons from a higher energy sublevel than a lower energy sublevel. All right, we've got another break again. So we're going from 5.31 to 0.74, a big jump in energy. 0.74, so we're talking about here the easiest electrons to remove. Where in an atom are the easiest electrons to remove? The electrons that require the least amount of energy. I'll give you 2 choices. The electrons that are close to the nucleus or the electrons that are far from the nucleus. That's right, the electrons that are further from the nucleus are less attracted to the nucleus and therefore easier to remove. Now we're talking about electrons in the third energy level. Well, which sublevel are we talking about? It must be the 3s. And it looks like this peak is the same height as the first 2 peaks. So again, I'm going to say that this peak corresponds to 2 electrons. So let's write then the electron configuration. So what atom does this photoelectron spectrum correspond to? This looks like it's the photoelectron spectrum of magnesium. So again, look at how they match up. Where did 1s2, 2s2, 2p6, 3s2 come from? It came from this graph and the energies required to remove electrons from the different sublevels in this atom. Let's take a look at the photoelectron spectrum for sodium. This is not in your notes, so you can either draw it in or just take notes on it. That's fine, either way. So on the test, it's not going to tell you what it is, but here it's telling you what it is. So again, let's start with the highest ionization energy, or here it's labeled on the x-axis binding energy, associated with those electrons being held to the nucleus. Always the hardest electrons to remove are those in the 1s sublevel. Got a big break in energy, big difference in energy, break in that x-axis there from 100 to about 7 megajoules per mole. That tells us that that next peak corresponds to electrons in a higher energy level. Next peak, not that much lower energy, 6.84 to 3.67. That tells us these electrons are in the same energy level, so we're still second energy level. This time the P sublevel. And then we have a pretty large difference in energy, 3.67 to 0.50. Again, telling us that that last peak corresponds to electrons in a higher energy level. Notice this time that the peak at 0.5 is shorter than the peak at 6.84. It's about half as tall. So I'm guessing that corresponds to 1 electron. So that's where the electron configuration for sodium came from. And again, it tells you, but try not to look at what this is. Let's figure out based on the photoelectron spectrum. So again, we're starting with the highest energy on the left. That peak corresponds to the 2 electrons in the 1s sublevel. Big jump in energy from 347 to 37, it looks like. So higher energy level. We go 37 to 29, not a big difference in energy. So that next peak, still second energy level electrons. We know there's 6 electrons maximum in the P sublevel. Big jump in energy from 29 to about 4. Not too much of a difference in energy from 4 to 2.38 or so. And again, we got a small peak there. Pretty big difference in energy, I guess, relatively speaking. Notice it's a lot more significant between first and second energy levels than it is between second and third, or in this case, third and fourth. And so we get the electron configuration for potassium. So that's how we read photoelectron spectra, these graphs, relative number of electrons versus ionization or binding energy. Need to be able to determine what an atom is given its photoelectron spectrum. There's other questions associated with these, but that'll give you a good idea of how to read them. All right, thanks for watching.